Hello everyone, welcome to the first lab of the semester. This first experiment is really just an overview of the equipment and their functions. Let's go ahead and get started. Down here is the function generator, which, as the name suggests, generates different waveforms which we will display on our oscilloscope above. Let's go over briefly the different things that you can do with the function generator. You can create different types of waveforms. You can see here on the left there's a sine, square, triangular, and then over on the screen we have the parameters that we can set. Looking at the sine wave, there is the frequency, the peak-to-peak voltage or amplitude, the phase, and the offset. But if you notice, we aren't really displaying anything, and that's because we're not outputting anything. So let's go ahead and output on channel 1, and we can see a waveform on our oscilloscope. Let's use the auto button. So this is the most useful button on the oscilloscope. It automatically zooms in and finds the waveform if it is to be found and displays it nicely. So as you can see, now it's nice and zoomed in. We have a good picture of it. Let's talk about some of the other features of the oscilloscope. There are two channels, a yellow and a blue, or channel 1 and channel 2. Right now we're only outputting one signal, so we only need one channel. But in the future, we will be using both. The waveform is being displayed on this grid, where the horizontal axes are in units of time and the vertical axes are in units of volts. And down here, we can see the scale that each of these increments are on. So what I mean is that for each step, you can see like these regularly shaped grid lines. Each horizontal step and each vertical step correspond to the units down here. For this is the horizontal axis. Each increment is in 250 microseconds, and each vertical increment is in units of 1 volt. And we can adjust this. So this is how we zoom in and out. These knobs up here adjust the scale of the waveform. So if I were to increase it, well, now the horizontal increments is in units of millivolts, 500 millivolts, so half the size, so it looks larger. And now if we change the increment so that the scale is 2 volts per grid line, now it looks smaller. And the same thing with the time, the horizontal axis, by making the increment smaller. So now it's 100 microseconds, the waveform looks bigger, and now it looks more squished together if each display is 500 microseconds, excuse me. Last thing, there are these position knobs. So you can either move it up and down or left and right. At its standard position, when you auto in and find it, the origin of the grid lines are at 0 volts. All right, now that I've done kind of a basic overview, let's jump into the lab. Following on, in part A1, it asks us to output a signal of 5 volts peak to peak at a frequency of 500 hertz. Let me go to our function generator and do just that. So, frequency 5. Now that our signal is being output, we want to use the grid lines to kind of measure how big the signal is, even though we haven't, we know it's being output, but in part 6 or number 6, it asks us to estimate the maximum voltage and the period just based off of our grid lines. Right now, the scale that I have it at, it's in units of 1 volt and in time units of 250 microseconds. If this is 0, it is 2.5 units high, so 2.5 volts by my estimation. In the horizontal direction, it is 1, 2, 3, 4, 5, 6, 7, 8 units for one full oscillation. So the period would be 2,000 microseconds or 2 milliseconds. Using the display is all well and good to get an estimation, but we can use the oscilloscope to actually measure the waveform. And if we click this measure tool up here, we'll do just that. You can see that there can be 5 things displayed simultaneously. Right now I went ahead and chose what I wanted to measure. So right now I'm measuring channel 1, peak-to-peak voltage, the period, the frequency, the max, and the root mean squared voltage. We can see that from our oscilloscope, the peak-to-peak voltage is around 5 volts. It's kind of fluctuating around that, but it's close. It's between 5 and 5.04. Our period is 2 milliseconds. Our frequency is right around 500 hertz. And actually, if I do this, does it make it happier? It does. Okay. So this is actually a good point. So you can tell that the units were kind of jittery. They were kind of bouncing around. And that's because when you're trying to measure something on the oscilloscope, you want to have the waveform as fully displayed as possible. And what I mean is that if it's kind of out of scale on our display, you can see that it doesn't give accurate results. So our input voltage is 5 volts peak to peak. That's what we set it to. And right now, because the wave is off scale, it's measuring 1.82 volts, which we know is not right. So something to keep in mind is that we should always have the wave clearly displayed. So we still right around 5 volts peak to peak, which it should be. 500 hertz, as it should be. Our V max is 2.44, 2.48. We know it should be 2.5, so close. And our root mean squared voltage is 1.72. Now, let's use the digital multimeter to also make a measurement for the root mean squared velocity. This other thing that I had down here in the corner is our digital multimeter, and we'll be using it again throughout the semester to measure components and measure voltages and currents. On the left here, we can see that we can measure current in units of microamps, milliamps, and 10 amps, which we will never use. We'll definitely be in this milli to microamp range. Over here, this is how we're measuring the values of our components. So we can measure resistance for resistors. That's what the omega is, the ohm. We can also measure capacitance. Over on the right, we can measure the voltage, either AC or DC. For this part, we want to measure the root mean squared voltage, excuse me. So that would be our VAC, or our AC current. And this is an AC current because it's an oscillating current. So we have from our digital multimeter that our root mean squared voltage is 1.774. So in the next part of our lab, we are going to be applying a negative 1.5 volt DC offset. Let's go down to our function generator. You can see down here where the offset is. If we type in negative 1.5, and then we want that in units of volts, we see that our waveform just got shifted down. And to see this, I can actually vary it using the knob up here. So if I decrease it back to 0, our waveform is back where it started. But increasing it down to our negative 1.5, we see that everything is now shifted down by negative 1.5 volts. If we were to use our measures on our oscilloscope, we see that the peak-to-peak voltage is still around 5 volts. Our period and our frequency are the same, but our V max is now this 960, which very close to, or 960 millivolts, very close to 1 volt. So again, let me just kind of center, it's still being offset, but let's go ahead and center our waveform so that it's being displayed fully. We can see that our V max is 1 volt, and now our VRMS is 2.24. That concludes the first part of the lab. Let's move on to A2, where we will demonstrate the Fourier function of our oscilloscope. So we now need to set our signal so that it is outputting at a frequency of 10 kilohertz. And we want to get rid of this DC offset. So let's set that back down to 0. And actually, for the Fourier feature, we actually want a zoomed out view of the waveform. It says in the manual to have at least 50 periods, 50 plus, so that's probably good. And now if we use the math function, so this button down here, we can use the Fourier transform of our signal from channel 1. I hope you can see this purple signal down here. I'll actually move it down, maybe a little to the left so it's a little off of the grid mark so you can see it. So we have now two signals. We have the original 10K hertz signal, and now we have this Fourier transformed version of that signal. One thing that you hopefully remember about Fourier transforms, if you transform just a plain sine signal, it turns into a delta function. And that's exactly what we're seeing here, this kind of really strong peak. Let's measure the frequency at which that peak is at. So if we go up here to cursors, and we want to move it into our manual mode so we can actually adjust where these cursors are. And we want to be measuring time. And we want to be measuring the math output, not the channel 1. Okay, and let's control cursor 1. So now these cursors are things that you can kind of manually adjust on the grid, and it'll give you the output exactly at that point. So right now we're measuring time, and so we can measure changes in time between our two cursors. So right now I'm moving cursor A, and you can kind of see it. So if I move it such that it's right over our peak, well, this gives us our frequency right at this peak. And hopefully it's no surprise that our peak in Fourier space is right at 10K kilohertz. So this is just for a regular sine wave, which again we can represent all waveforms as linear combinations of orthogonal functions, which the sine waves are, and it's often the one that we use to create other functions with. That's actually exactly what is happening with our function generator. We're still all using these plain sinusoidal sine waves to make more complicated ones. And to see that, instead of just outputting a sine wave, let's output a square wave. Again, it's a little, I don't think I can, yeah, not when it's in this mode. Although, I can back out. Let's turn this off. And let's auto it. So we can see here a plain square wave. And so if we do the same thing, make a whole bunch of them, use the math function. Well, now that square wave is a linear combination of sine waves. And in the Fourier mode, we can see the frequencies of those different sine waves that are making up this one signal. And the peaks of these waves are, or like how high the delta function is, corresponds to the amplitude or the strength of that signal, the voltage of that signal. Unsurprisingly, our square wave is this linear combination of a bunch of sine waves. And I can measure where these peaks are at. So we still have one at 10K, but then our next highest peak is at around 30K, and so on. Let's take a closer look at this square wave. So I'm going to take off the math function, and we're still at 10K hertz, so I think I'm actually going to make it a bit of a lower frequency. So let's change it back down to 1. Whoops, didn't like that. 1 kilohertz. Here we have a square wave. When we're this far zoomed out, when we have our time increments and units of this 250 microseconds, it does look like a complete, vertical transition between our two peak voltages. So, it goes from negative 2.5 volts to positive 2.5 volts almost instantaneously. We should know that nothing really happens instantaneously. If we were to zoom in on this waveform, we start to see, so now we were in the scale of 250 microseconds. Now I'm changing it such that, let's do this. Now each of the grid lines, each of these horizontal increments is in units of 5 nanoseconds. It's really zoomed in. And now we don't really see a definitive square wave. Like, this is not an infinite slope. There is a definite, curve to it, which there needs to be. There is no perfectly infinite things in nature. Actually, if I back up just a little bit, touching on what we just saw on the Fourier mode, we can still see like the linear combinations of sine waves are still present even at this kind of, really zoomed out perspective. So that's where these are coming from, because it is this linear combination of different sine waves. All right, but now in the lab manual, we are asked to measure the time that it takes to go from our lowest point, or our negative, our minimum voltage, to our max voltage. And we are just going to be using the display to estimate that. So let me shift my position. I'll shift the waveform so that I can roughly line up where the wave begins to ascend. I'll go ahead and say that, let's see, the time it takes to reach its maximum point would be here at this peak. And so that time would be what? 1, 2, 3, a little less than 4, like 3.5 increments. So around 17.5 nanoseconds if we're using this 5 nanosecond scale. Like I did with the cursor mode on the Fourier transform part, I can also get a much more accurate measurement, because this is not something that the oscilloscope can measure. I mean, it doesn't give the rising time of our waveform, and that's just, but we can use tools within the oscilloscope to get a pretty good reading. So again, let's set up our form, and then we want to measure time, and we want to be measuring channel 1. And so we can adjust our cursors and put it exactly where we think our minimum value is, or right where the slope begins to turn upwards, and put this exactly where our peak is. So now it gives us the values at cursor A and at cursor B, but over here this delta t gives us the time between the two. From where I put the cursors, 17.4 nanoseconds for the wave to rise from its min value to its max value, which is close to our estimation on the display. Let's move on to part A3. For this next part, we will need to be outputting 2 signals from our function generator. So let's do that. Right now I have a 1 kilohertz 4 volt peak to peak sinusoidal waveform, and let's go to channel 2. And by default, it's also giving out a 1 kilohertz 4 volt peak to peak signal. So let's connect our probe. That's centered, and then output that signal, and then auto to find it. Great. So we are displaying two signals, and the auto will shift them up and down to so they can be displayed simultaneously. So over here on the left, this is will show you where your 0 volt line is at. Previously, since there's only one signal, it was right at the origin, so we didn't have to worry about it. But now these two things are kind of independent. And we can see here that the time scale is going to be the same for both. So sometimes if your signals aren't close to the same frequency, you really can't see one or the other. But now you can adjust the two channels voltage size independently. So for whatever reason, the auto made it so that it was different from the other one. But if we now adjust our positions for both of our signals, such that they're both kind of at this center mark, we can see that they are indeed the same signal. They overlap completely. They're both being at scale 2 volts for each increment, and both at 250 microseconds. We are asked to introduce a phase shift in one of our signals and see how it changes. So right now, I will choose channel 2 since I'm already on it. So I'll go to phase, and I'm going to start to increase the phase, and we'll see how it affects our signal. So at a 0 phase shift, both of these signals are completely in phase. So now if I start to introduce this shift, we can see, and actually I'm going to make the signal slightly bigger. So now the scale is at 1 volt instead of 2 volts. Here we are at 45 degrees phase shift, and I will increase to 90. Now I'll increase all the way to 180. And so at 180 degrees, they are completely out of phase, and if these two signals were to be added together, they would deconstructively interfere with each other, and we wouldn't really see a signal at all, as opposed to when they are at 0 degrees, they would constructively interfere, and then you would see a signal with a larger maximum voltage. So this is at 180 degrees. Let's increase our phase shift again back to 360. And unsurprisingly, now that we are at 360, the waveforms are completely in phase again. Let's go ahead and set our phase shift back to 0. So in this next part, we will be changing our display of our oscilloscope. Up until this point, we have been displaying voltage on the y-axis, time on the x-axis, and we just saw that you can have two waveforms, each with their kind of different scaling for voltage, but still both on this, voltage versus time axes. We can actually combine two waveforms. So if we change from our YT format to our XY format, now we are no longer displaying time as one of our axes on our display. So right now we see this vertical line, or not vertical, this 45-degree angle line, and it's the combination of both signals. So let's remove channel 1 from the oscilloscope so that it's no longer getting that signal, and we see that with only the channel 2 input, we see just a vertical line. So that means our y-axis is the channel 2 input, and the other axis is probably the other one. So that's the way that this is set up. Now let's reduce the frequency of our channel 2 output by a lot, down to 1 hertz. So right now they're both at 1K or 1000 hertz. So if we go to channel 2, we go to frequency, 1 hertz. And we should start to see it oscillate. I think it's still having some trouble. So we're going to decrease our frequency even more. So hopefully this becomes more apparent. It's still a little jittery. Let's go down to 100 millihertz. That's a lot better. Okay. So, oops. Still. All right. So now that we've decreased the frequency of one of our inputs to something that on a scale that we can see, we see that the signals will oscillate in time. I mean, they're still being added together in this format, but previously, because they were at the same frequency, it looked like a still image, but in fact they add together such that we see this sort of process. I'm gonna go ahead and set our channel 2 frequency back up to 1 kilohertz so that we're back at this familiar combination. And now I'm going to adjust the phase again and see how we saw how phase shifting 2 different signals and how it looked. Now let's see how, when they're combined in this way, the phase shift affects the output image. So once again, I'm on channel 2, and I will slowly start to increase a phase shift. So now channel 2 has a phase shift of 45 degrees, and as we increase to 90 degrees out of phase, see a circle start to appear. Let's increase to the other 135. Okay, we see an oval in the opposite direction, or kind of opposite orientation. And then now that we're at 180 degrees out of phase, whoops, 180, we see once again where it was deconstructively interfering. Well, if we were to add the 2 waves together previously, they would deconstructively interfere, so we would just see a straight line. Now we are seeing this kind of same as 0 degrees, but now it's kind of in the opposite direction. And I'll just continue. So at 225 and at 270, we once again will start to see a circle appear, and then as we continue going all the way back to 360, we are back at our original position. And if I was maybe you saw it during the video, but it almost looks like an actual image of, it looks like a 2D image of something like a ring rotating, if it is kind of a smooth enough transition between phase shifts. All right, so last part of this section, we want to set our phase back to 0, and we want to increase our channel 2 frequency to 2K. Where now we have this new symbol, and you're asked to draw it. And now we are going to very slightly increase, where previously in this last part we had a huge difference in frequency. So we can see like this very small oscillation. Now we're going to adjust one of the channels by a very small amount and see what happens. So I will change I will increase the frequency of channel 2 by 1 or 0.001. That's still really fast. So let's go 2.0001 kilohertz. We can see it starts to rotate. Well, it appears to rotate. I mean, it's kind of what I was talking about earlier with the ring. If I was able to move the phase, it would kind of look like a ring that's rotating. Now with these very slightly shifted phases or frequencies, it does have this appearance of rotating, and it kind of has this saddle horse appearance, at least to me. So if I decrease, let's put it back to 0. So let's increase it again. And now, set it back. Now let's try decreasing it and see if you can see a difference. It's a little bit difficult because it is like a, just a 1D line on a 2D surface. So we think it's in 3D, but or has the appearance of being 3D to us, but it can still be a bit mind-boggling. And then, if you were here in class, you could kind of play with these different waveforms and frequencies, and you get tons of different shapes and combinations. I'll increase it by, whoops. But these whole number kind of ratios of frequencies are more or less these still images, but slightly increasing or decreasing our phases, or I'm sorry, I keep saying phases, our frequencies, so that they're slightly out of this kind of state. We get this appearance of movement, of motion. So pretty interesting stuff. That concludes this kind of overlook to the oscilloscope. In this next part, we will be building a simple circuit and measuring the current and voltages and the resistance of the various components. So this is the other big kind of piece of equipment that we'll be using in pretty much all of our labs. And it has a lot of bells and whistles and doodads and whatnot, but the main component is our breadboard, and these are very things that we can add into circuits that are easily accessible. And as they appear in later circuits, I will make note of them and describe what they do. But just brief overview, these are variable resistors, resistors that you can change. These are more for digital circuits. This is like a number output and diodes. A switch down here, various buttons that if you press, it allows a connection, a transformer, and then over here on the right, there's a photo transistor, so if a light is shining on it, it'll be in the on state, and a buzzer, and a speaker down here. But right now, all we have is just a circuit with 3 resistors and a DC power supply, which is off screen over here. I will show it afterwards. Let me explain the breadboard and how it works. So for the breadboard, you see these 6 columns, and you notice that there are these rows in the middle, and then there's these ones on either, both above and below. So the thing to know is that these rows in the middle, each row is isolated from the other one. So only the 5 holes in each row are connected. But this row is not connected to this row. We would need to put a wire between one row and any other row for it to continue the circuit and have current flow through each of these rows. The exception is these rows at the top and bottom. So this entire row, these 6 columns worth of rows, are all connected to each other, and the same thing with, and the same thing with this row down here. And that's for where we introduce our power supply. So the idea is that we have power going to this the positive end of our power supply coming into this top row, and if we need to add that into our circuit, well, we can always just jump from any point in this top row. And to complete our circuit, if we need to bring it to ground, same thing, we can always bring anything from up here to ground and it will complete the circuit. So I've constructed the circuit from your lab manual, and I've arranged it in such a way that it sort of resembles what we see, the picture that we see in the lab manual. So you can imagine our potential being here on the left, and so going from positive to negative, we have current coming in, going down, passing through our 1,000, quote unquote, 1,000 ohm resistor, and then coming, so that's connecting from here to here, and then we get to this this junction where these two 470 resistors are in parallel, so current can either flow down this way or jump over to here and flow down this way. And then eventually they reconnect, so this is just a wire connecting them back together, and then this will bring us to ground, and the circuit is completed. This is what it looks like in the constructed state. I'm going to take out the pieces and measure their resistances so that you can take your measurements. I'll take this moment to go over the power supply and measure our resistors before we start making our measurements. This is our DC power supply, and right now I have it connected to the circuit. If I turn it on, so you can adjust the voltages that you want to have for whatever circuit you're making. And down here, so that's what's up here. I've already set it to 5 volts, but I can adjust it as such. Down here is our amps, and as you saw in the manual, or hopefully you read, it said to put a current limit of 10 milliamps, and that's good practice for whenever you're doing these kinds of circuits or anything that you're building, because of course current is a thing that you have to be wary about. In this lab, we would never get anything approaching several milliamps, so we always put a current limit of 10 milliamps. Usually for these circuits that we build in this lab. And so right now we can see that our current circuit is pulling roughly 0.003 amps or 3 milliamps, although this is not a very accurate way of measuring current. If we wanted to measure current, we'll use the digital multimeter. If I were to increase the voltage, the current would increase. If I increase the voltage to a certain amount such that that 10 milliamp threshold was met, then I couldn't increase the voltage anymore. It would stop. And those are the some the safety practices that we have that we always use when in the circuits lab. My guess is in the future videos that I probably won't, unless we need to measure something off the DC power supply, I'll just say that it's at the 5 volts, and I probably won't have it on screen, but that's what we have here. Let's measure the resistors that we're going to be using for the circuit. And so I'm just going to pull them out, use our digital multimeter to measure them. So let's set it to measure resistance or capacitance. We'll take our 2 ends. So right now we have our resistor. Let's see if we can do this. There it is. Our resistor. And I guess this is a good moment to talk about the color code for resistors. So this is a 1,000 ohm resistor, and it's designated by, the rough resistances are designated by the color stripes that you see on it. For all the resistors in this class, there are going to be 4 lines. The first 3 designate the resistance of our resistor, and the last one kind of gives the tolerance, or the plus or minus it's accurate to plus or minus, whatever value. The color combination or the color code goes like black, brown, and then through the colors of the rainbow, red, orange, yellow, green, blue, violet, and then it ends off with gray and white. So 0 through 9, black is 0, brown is 1, going through the other colors where white is 9. And so right here, these first two colors, this brown and black, that gives you a 1 and a 0. And so those give you the first 2 digits of your resistance. And the third one gives a power to 10 that the first 2 digits are raised to. So in this one, since it's, like I said, brown and black are 1 and 0, so it's 10. Put those numbers together, it's 10. And that's times 10 and, let's see, red. Ooh, please focus. Focus. Red is 2, so it's 10 times 10 to the 2, so 10 times 100, which is 1,000. So this is roughly 1,000 ohm resistor. And so looking at our digital multimeter, it is close to 1,000. It's 0.983 kiloohms, or roughly 1,000 ohms. So we see yellow, purple, brown. So yellow's 4, purple is 7, and brown is 1. So 47 times 10 times 10. 10 to the 1 is 10. So 470. And reading off the digital multimeter, it's 460. I'm sorry, well, okay. It's 460 ohms. What it's actually reading is, you can, see it? It's 0.460 kiloohms. So the range will change on the side. That's R2. And let's measure R3, which again is another 470 ohm resistor. And we see a similar value of 459 ohms, or 0.459 kiloohms. Okay, so those are our measurements for our resistor. And now we'll reconnect it to the circuit and make those voltage and current measurements. All right, so let's go ahead and make our measurements with our digital multimeter. In part 5, or question 5, we were asked to record the voltage drops between, or at VA, VB, and VC. So the important thing to know when measuring voltages is that it needs to be in parallel with whatever you're trying to measure, because you're interested in a voltage drop over the circuit. Wherever we, for instance for VA, we want to measure the voltage drop between, just upstream of that first 1K resistor and ground. So if we were to add our multimeter in, and then go ahead and add the negative in to ground. Let's see, just put it in grounded there. We have at VA, or our voltage at position A, is 4.96 volts, which hopefully makes sense because really we're just measuring the voltage output of our power supply, not after any resistors. This is the voltage drop over the entire circuit, and since we are supplying a full 5 volts, then at the beginning we have, it should be close to 5. Okay, so now let's measure the voltage just up or just downstream of R1. I could connect it right here, and we see that we're measuring the potential drop from here down to ground. And from this point, we're seeing that our potential is 0.942 volts. Finally, we'll measure from just downstream of the capacitors and ground. And really, this is really close to zero, and ideally it should be zero, because the potential drop between essentially 2 points that are at ground, well, that's going to be zero. So we're getting close. It's like 0.2 millivolts. So those are our three voltage measurements. Now let's measure current. And unlike how when we were measuring the voltages, we needed to have our digital multimeter in parallel, for measuring currents, we need to have our multimeter in series with our circuit. And you can think about this like the current needs to flow through the multimeter for it to actually measure it. So it needs to be in line with our circuit. So in order to make these measurements, we actually have to break our circuit and then add in our multimeter. And that's exactly what I'm going to do. So if we want to measure I1, the current going through the first resistor, we would measure just downstream of that resistor, just right after it. So we can attach the positive end of our multimeter to the actual resistor itself, this metal bit. And then the negative end, I just have a little wire, and I'll poke that in to where the resistor actually used to attach into. And so now our multimeter is in line, and we can see that the current going through R1 is 4.06 milliamps. I have it on the milliamp scale, and you can actually see the units up here. So 4.06 milliamps for our I1. Now let's measure the other two. And I need to reconnect it. And R2 is this first 470 resistor. So once again, I will unattach it, attach the positive end just right after, and I will attach the negative end to where it used to be put in. Okay, so the current going through R2 is 2.02 milliamps. And let's do the last one. Oops, sorry, didn't mean to bump it. So connect that one in, unattach, attach our multimeter, bring in the negative end to where it used to connect. And there we see that we get the exact same reading of 2.02 milliamps for I3. And those are all the measurements that we need for this experiment.